Hello class, this is lesson 13.3, the base E. So this lesson actually builds on the two previous lessons in which we talk about exponential growth functions and then exponential decay functions. We are still looking to see transformations and then looking at reference points so that we could create an equation that goes with the graph. And then we do want to also look at modeling just like how we did with exponential growth and exponential decay. So some of you guys might be asking, what is E? So let's kind of talk about what E is. E is a special number. Let me show you my notes. So what we're looking at is how can we graph exponential functions where the base is E. Now, E is actually derived from this equation, which is 1 plus 1 over x to the x power. Now, what happens is as x increases, this approaches a number, and that number is E. E is actually called a constant, and it is approximately 2.718, and it goes on forever. So in geometry, you guys heard of pi, which is 3.14, and again, it goes on forever. This is similar in that E is a number. So E is 2.718. And in your calculators, there is a function E, so you don't have to worry about typing in the value of E. Now, because E is greater than 1, meaning because 2.718 is bigger than 1, that is going to be an exponential growth function. So these graphs are going to behave like an exponential growth function where you see it increase. So starting from the left to the right, these graphs are going to go up. And then we are going to be looking at two reference points. The first one is 0, 1, that's the y-intercept. And the second one is 1e. And then our transformation equation, so that it looks like the other ones, would be this. So g of x is equal to a times e to the x minus h plus k. Now a, h, and k do the same things as they did for exponential growth and exponential decay. We just have to remember what they do. So let's go on to comparing parent functions and comparing transformation functions. So let's look at the first example. We have a parent function of f of x is equal to e to the x power, and then we have a transformation function which is g of x equals negative 3 times e to the x plus 1 plus 4. So what we need to do is identify what a, h, and k are. So a is negative 3, h is negative 1, and k is positive 4. So because a is negative, that's going to cause a vertical reflection. Because a is greater than 1, because 3 is greater than 1, that's going to be a vertical stretch. And then because h is negative 1, that means we're translating 1 unit to the left. And then if k is positive 4, we're translating 4 units up. So let's look at what they wrote as a solution to this problem. The transformations that have been performed on g of x are a reflection across the x-axis, so that's the vertical reflection part. Vertical stretch by a factor of 3, translate 1 unit to the left, and translate 4 units up. So that's what we got. Then let's look at another example. So the parent function, again, is f of x equals e to the x power, and then the transform function is g of x equals 1/2 times e to the x power minus 8. So we notice that a is a half, and k is -8. And if a is a half, that's going to be a vertical compression. So because a is between 0 and 1, the rule tells us that it is a vertical compression. And then if k is -8, then that means that we're translating 8 units down. And their solution was the transformations that have been performed on g of x are a vertical compression by a factor of a half and translate 8 units down. So next, I want you guys to try a problem on page 30. So again, you guys are comparing the parent function, and you guys are comparing the transform function. So let's identify what a is, what h is, and then what k is. A is -1, h is -2, and k is -3. What happens if a is negative? That's a vertical reflection. What happens if h is -2? That is translate 2 units to the left. And then if k is -3, that is translate 3 units down. Now, some of you guys might be asking, why isn't there a vertical stretch or vertical compression? And that is mainly because A is -1, so the negative makes this a vertical reflection, but when A is 1, that is neither a stretch or a compression. So these are our 3 transformations that occurred. Okay, next we're going to be looking at reference points of the base E functions. So similar to the last lessons, I actually wrote them down here as well. So let's look at our parent function reference points. The first reference point is 0, 1. And this is also the y-intercept, 0, 1. The second reference point is 1e. And then the asymptote is y equals 0. And then for the transform function, the first reference point is h comma a plus k. The second reference point is h plus 1 comma ae plus k. And then the asymptote is y equals k. So what we're going to be doing is we're going to be looking at example 2 on page 31. So this example right here. Okay, so when we're looking at these problems, the first thing that we want to do is we want to look for the asymptote. So we want to look for the horizontal asymptote because that tells us what k is. So if y is equal to 4, then k is equal to 4. So that's the first piece of information. The next piece is the first reference point. The first reference point is 4, 6, and we're comparing this point to the point in the equation, which is h comma a plus k. So let me show you here. So 4, 6, and then h comma a plus k, so h is equal to 4. And then a plus k is equal to 6. So from here, we could actually solve for a by plugging in 4, because k is 4, a is equal to 2. So k is 4, h is 4, and a is 2. And plugging in the equation, we get g of x equals 2 times e to the x minus 4 plus 4. Okay, so next I want you guys to try another problem. So again, try to pause the video and then take the time in identifying all the points, but I'm just going to be working this out right now. So let's start with the horizontal asymptote is at y equals 2. So that means k equals 2. My first reference point is 3, 1. And I'm comparing that to the equation, which is h comma a plus k. So h is equal to 3. And then a plus k is equal to 1. And if I substitute 2 for k, I get a plus 2 equals 1, and a is equal to negative 1. So now that I have all of these pieces of information, I'm going to plug it into my equation. So it will be g of x is equal to negative 1, because that's what a is, times e to the x minus 3 plus 2. And we actually don't need that negative 1 in front. Actually, we could just leave it like that. That's fine. But yeah, this would be your solution. Okay, so now let's look really quickly at modeling exponential functions with base e. So we did talk about modeling with exponential growth functions and exponential decay functions, but now let's look at how we could model with the base e. So remember that this is our parent function, f of x is equal to e to the x power. And then the equation that we're going to use to model is this one. So g of x is equal to e to the cx power. Now, c is a constant. That's a number that could be positive or negative depending on what the problem is. So we are going to be using g of x equals e to the cx to model exponentials with base e. So let me walk you through the first word problem example. Okay, so let me send through this. So the first problem is the Dow Jones Index is a stock market index for the New York Stock Exchange. The Dow Jones Index for the period 1980 to 2000 can be modeled by VT equals 878 e to the 0.121 t power, where t is the number of years after 1980. How many years after 1980 will the Dow Jones reach 3000? Graph the function on a graphing calculator or at desmos.com and use the graph to make the prediction. So we're given our function, and then we're given a value that we want to find out how long it's going to take. So we're going to graph these two equations on Desmos. So let me switch to Desmos. So we're going to write v parentheses t is equal to 878, And let's see if there's an E button here. Not sure. There it is. And then let's put this to the power of 0.121 t. So then my other equation would be v parenthesis t is equal to 3,000. Okay, and then let's zoom out. So there is the exponential growth function, and then we're looking at 3,000, and that is right here. Okay, so zooming in, and if I click the intersection point, it will take 10.155 years to reach 3,000. And that's what they got. Yep, right there. Okay. Next, let's try a problem on our own. So let me kind of walk you through this one. A paleontologist uncovers a fossil of a saber-toothed cat in California. The paleontologist analyzes the fossil and concludes that the specimen contains 15% of its original carbon-14. The percent of the original carbon-14 in a specimen after 2 years can be modeled. Nt equals 100e to the negative 0.00012 t power, where t is the number of years after the specimen died, using the graphing calculator or Desmos to determine the age of the fossil. So this is our first equation that we're going to graph. But then you guys might be asking, what is the second equation? What are we trying to find? So what we're actually trying to find is, what is 15% of the original 100? And if I do some side math here, 15% of 100 is equal to 0.15 times 100, which is 15. So the other equation that we're looking for is when nt is equal to 15. So now let's graph both of these on Desmos. So the first one I'm going to graph is n parenthesis t is equal to 100 e to the negative 0.00012 t power, and then nt is equal to 15. So let me zoom out. Okay. So I have a graph right here, and then again I'm looking for the intersection point. So it's kind of hard to see. So I just have to keep zooming to see when the purple line and the green line are going to intersect. And so I'm assuming it's somewhere around here. really hard to determine. Okay, I'm just gonna estimate this. So I'll just say something around here. Hold on, let me just try to zoom out a little bit more. Okay, right here it is. It will take 15,809 years for it to reach 15. So T is equal to 15,809 years. Okay, now let me go back. Okay, so that pretty much answers the question. But yeah, what we're doing is, again, graphing this equation, and seeing where the two lines intersect. All right, so that pretty much ends lesson 13.3. Again, work on the problems on the homework on the checkpoint, and then submit those through Google Classroom. And again, if you do not have a packet, try your best to write the question and answer and show all work on a separate sheet of paper. Thank you.